Welcome to module 4 of chapter 2. In this module, we will introduce congruences, we will prove different properties of congruences, and we will see few applications of congruences. Finally, we will prove Fermat's little theorem. In this module, we will introduce congruences. The learning objectives of this module are introduction to congruences and its properties, system of residues, applications of congruences in divisibility, Fermat's little theorem. First, we define what a congruence means. Let n be a positive integer and a comma b belongs to Z. Then a and b are said to be congruent modulo n, or a is said to be congruent to b modulo n, denoted a is congruent to b mod n if n divides a minus b. That is, there exists k belongs to Z such that a minus b is equal to k into n. Since 1 divides every integer, so any two integers are congruent to modulo 1. It is because if you look at the definition, a is congruent to b mod n if n divides a minus b. That is, if you take any two integers, their difference is again integer, so it is divisible by n. So, one is any two integers are congruent to 1. Two integers are congruent to modulo 2 if and only if either both are even or both are odd. Let a belongs to Z and b and n belongs to n, then by division algorithm we have a equal to n cube plus r, where 0 is less than or equal to r is less than n. In other words, a is congruent to r mod n, since r is a remainder. So, it is one of the integer from 0 to n minus 1. So, every integer is congruent to exactly one of the element from the set. So, this set is called set of least residues modulo n. So, for every given n we have a set, the set is called set of least residues of that particular integer n, positive integer. So, here the set contains 0, 1 up to n minus 1. Fix a positive integer m and let b1, b2 and so on bm be any collection of m integers that are congruent to 0, 1, 2, 3 and so on m minus 1 in some order. Then the set b1, b2 and so on bm is called complete system of residues of modulo m. It is easy to see that set of least residues is also a complete system of residues, and the set of complete system of residues is not unique. In fact, it is easy to see that any set of m integers is a complete system of residues if and only if no two of them are congruent to modulo m. So, we are going to prove an important theorem which contains many properties of the congruences. Let m greater than 1 be a fixed positive integer and let a, b, c r belongs to Z, then the following are hold. The first one is a is congruent to a mod m, and the second one is if a is congruent to b mod m, then b is congruent to a mod m. Third property is if a is congruent to b mod m and b is congruent to c mod m, then a is congruent to c mod m. These three properties will make congruences as an equivalence relation on Z. So, congruences will help us to find an equivalence classes of Z. If a is congruent to b mod m and c is congruent to d mod m, then a plus or minus c is congruent to b plus or minus d mod m, and also ac is congruent to bd mod m. If a is congruent to b mod m, then a plus c is congruent to b plus c and ac is congruent to bc mod m. If you look at the statements of 4 and 5, in the 4 we given two congruences in the hypothesis, here we given only one hypothesis, that is a is congruent to b mod m. Then we are stating that a plus c is congruent to b plus c mod m and ac is congruent to bc mod m for any integer c belongs to Z. If a is congruent to b mod m, then a power n is congruent to b power n mod m for any integer m. So, this is the result we will going to use very frequently, and if AC is congruent to BC mod m, then A is congruent to B mod m by D, where D is equal to GCD of C comma m. If A is congruent to B mod m and K divides m, then A is congruent to B mod K. Ninth one, if A is congruent to B mod m and C belongs to N, then Ca is congruent to Cb mod Cm. Finally, if A is congruent to B mod m, then the integers A, B, m are all divisible by D greater than 0, then A by D is congruent to B by D mod m by D. So, we are going to prove all these parts of this theorem one by one. The proof of the part 1, since m divides 0, we know that every integer divides 0. So, 0 can be written as a minus a for any integer a. So, a is congruent to a mod m. So, for any integer a, we have a is congruent to a mod m. So, this is also true for any integer m. So, congruence relation satisfies a reflexive property. Now, the proof of part 2, here a is congruent to b mod m. So, by definition what do you mean by that? M divides a minus b. So, that means that a minus b is equal to m into q for some q. Thus, m also divides m into minus q. It is because m into minus q is simply a multiple of m. So, m divides m into minus q, but m into minus q is nothing but b minus a. So, by definition what we have is m divides b minus a. So, by definition b is congruent to a mod m. So, we proved that whenever a is congruent to b mod m, b is also congruent to a mod m. So, this says that congruence satisfies symmetric property. So, there is no wrong in saying a is congruent to b mod m or b is congruent to a mod m. Then now the proof of part 3, this is a transitivity property. Here if a is congruent to b mod m and b is congruent to c mod m, then by definition m divides a minus b and m divides b minus c as well. So, hence by linearity property m divides a minus b plus b minus c, that is equal to a minus c. Thus, we have a is congruent to c mod m. So, with this we proved transitivity property also. So, the part 1, 2, 3 proves that congruence is an equivalence relation on the set of integers. Now, proof of part 4, since a minus c is equal to a plus of minus c. So, it is sufficient to show that only the plus case, that is by assumption m divides a minus b and m divides c minus d. Therefore, by linearity m divides a plus c minus b plus d, that is which is also equal to a minus b plus c minus d, and m divides c into a minus b plus b into c minus d. So, we will get a c minus b d. Hence, a plus c is congruent to b plus d mod m as well as a c is congruent to b d mod m. Now, here I request you to go back to those slides and look at again what are the statements, otherwise we may forget what we are proving here. So, now the proof of part 5, since a is congruent to b mod m, then m divides a minus b, thus m divides c into a minus b for any integer c. So, and also m divides a plus c minus c minus b, that is equal to a minus b. So, we have a plus c is congruent to b plus c mod m as well as a c is congruent to b c mod m. This result what we had to prove is, if a is congruent to b mod m, then a plus c is congruent to b plus c mod m and a c is congruent to b c mod m. Now, by using these, now we will prove an important result, that is whenever a is congruent to b mod m, then a power n is also congruent to b power n mod m for all n. We will prove this by induction on n. If n is equal to 1, the result is true by assumption that a is congruent to b mod m. Assume that the result is holds for n equal to k, that is a power k is congruent to b power k mod m. Since a is congruent to b mod m, thus a into a power k is congruent to b into b power k mod m, that is this is follows from our previous result, or equivalently a power k plus 1 is congruent to b power k plus 1 mod m. Hence, by principle of mathematical induction, the result holds for all numbers n belongs to n. Even this can be proved by different ways also. By using binomial theorem also we can prove. Now, proof of part 7, as AC is congruent to BC mod m, we have m divides AC minus BD. So, that is equivalent to C into A minus B. Thus, C into A minus B is equal to m into k for some integer k belongs to Z. Since C comma m equal to D, that means that GCD of m C comma m is D, that means that C is a multiple of D and m is a multiple of D, that is C is equal to D into k1 and m is equal to D into k2 for k1 k2 two integers. Thus, dk1 into A minus B is equal to dk2 or k2 divides A minus B, as GCD of k1 k2 equal to 1. Thus, A is congruent to B mod k2, which is equal to m by d. Similarly, we can prove the parts of 8, 9 and 10. So, now with this we proved 1, 2, 3 up to 7. Now, with this idea we can, it is easily to prove parts of 8, 9 and 10. These proofs left to the reader. Congruences is a powerful tool introduced by Gauss. It enriched number theory in a very big way. Congruences introduced very new number systems. For example, fields with a finite number of elements, fields containing infinite number of elements, but non-zero characteristic. With this, there is a lot of advantage that many problems which are very difficult to solve earlier can be solved by reducing the problems to finite fields. Of course, we not defined what is a field or finite fields, but these congruences help to create a new objects like these. Now, we are going to see few applications of congruences in the divisibility of integers. Now, we will see few applications of congruences. Before that, we will define one definition. Let m belongs to n be given. For each a belongs to z, the residue class or congruence class or equivalence class of modulo m, denoted as within brackets a or a m, is defined as a is equal to x belongs to z such that x is congruent to a mod m. This is a set of all integers which are congruent to a modulo m. That is, the set contains 0, 1, 2, 3 and so on m minus 1. These sets residue classes will going to partition the entire z. So, it is denoted by zm. To try to look at each element of zm is a set. So, zm is a set of sets. This zm itself has a nice properties. Here we are not proving, so one can refer that this forms a group under addition modulo m and so on. So, now we will look at the first application of the congruences. Let p of x is equal to summation k equal to 0 to m c k x power k be a polynomial function of x with integral coefficient c k. If a is congruent to b mod n, then p a is congruent to p b mod n. It may happen that p a is not equal to p b, but p a is congruent to p b mod n. That means that n divides p a minus p b, or otherwise p a and p b will leave the same remainder if we divide by n. Now, we look at the proof for this theorem. Since a is congruent to b mod n, we have a power k is congruent to b power k mod n. This we proved in the properties of congruences. Consequently, c k into a power k is also congruent to c k into b power k for k equal to 0, 1, 2, 3 and so on m. Adding all these m plus 1 congruences, we will get p a is equal to summation k equal to 0 to m c k a power k, which is congruent to summation k equal to 0 to m c k b power k, which is equal to p of b mod n. So, we proved this theorem. So, now we will use this to prove some of the important divisibility properties. That is, if p of x is a polynomial with integer coefficients, we say that a is a solution of the congruence p of x equal to 0 mod n if P of A equal to 0 mod n. If A is a solution of P of x congruent to 0 mod n and A is congruent to B mod n, B is also solution of P of x congruent to 0 mod n. This proof is easy to see, so we left the proof to the reader. So, we will prove the first property or important applications in divisibility. Let m is equal to am 10 power m plus am minus 1 10 power m minus 1 and so on 10 an 10 a1 plus a0 be a decimal expansion of the positive integer m 0 less than or equal to ak less than 10, and the set s is equal to, we will let s is equal to a naught plus a1 plus and so on plus am, then 9 divides m if and only if 9 divides s. What it says is a number is divisible by 9 if and only if sum of the digits is divisible by 9. So, how to prove? Let P of x equal to summation k equal to 0 to m a k x power k, then P of 10 is equal to m. So, that is the decimal expansion, and P of 1 is equal to s. It is easy to see, if you plug in 1 in this polynomial P of x, then x value 1, then we will get sum of all the coefficients, that is exactly s. But we know that 10 is congruent to 1 mod 9, hence in the previous result P of 10 is congruent to P of 1 mod 9, thus we have m is congruent to s mod 9. But how this is related to 9 divides m if and only if 9 divides s? Since m is congruent to s mod 9 implies that 9 divides m minus s. So, whenever 9 divides m, then 9 automatically divides s. Similarly, 9 divides s, then 9 automatically divides m. So, we will look at another application of congruences. Let n is equal to am 10 power m plus am minus 1 10 power m minus 1 plus and so on plus 10 a1 plus a0 be a decimal expansion of a positive integer n, where ak greater than or equal to 0 and less than 10. Let t is equal to a0 minus a1 and so on plus minus 1 whole power m am, then 11 divides n if and only if 11 divides t. This statement is similar to the previous statement, only difference is there we used 9 divides m if and only if 9 divides s, here 11 divides n if and only if 11 divides t. The proof follows in a similar fashion. Again we will take, let P of x be a polynomial summation k equal to 0 to m a k x power k, then P of 10 is equal to n and P of minus 1 is equal to t, which is easy to see. Now, the key point is that 10 is congruent to minus 1 modulo 11. So, hence P of 10 is congruent to P of minus 1 mod 11, which implies n is congruent to t mod 11. Now, we will prove one of the important theorem in number theory called Fermat's little theorem. So, before proving the theorem, we will motivate you. It is easy to see that 1 power 4 is congruent to 1 mod 5, 2 power 4 is congruent to 1 mod 5, 3 power 4 is also congruent to 1 mod 5, 3 power 4 is 81. So, 81 is congruent to 1 mod 5, 81 minus 1 is divisible by 5. Similarly, 2 power 4 is 16, 16 minus 1 is divisible by 5, 4 power 4 minus 1 also divisible by 5, whereas 5 power 4 is congruent to 0 mod 5, 6 power 4 again congruent to 1 mod 5, 7 power 4 similarly congruent to 1 mod 5, 8 power 4 and 9 power 4 also respectively congruent to 1 mod 5, whereas 10 power 4 is congruent to 0 mod 5. This continues. Here we are doing modulo 5, that is 5 is a prime number. Now, this can be, is it possible to extend this to all prime numbers? Yes, that is the Fermat's little theorem. That means, whenever you do a power p minus 1, then it is congruent to 1 mod p whenever p does not divide a, whereas if p divides a, then a power p minus 1 is congruent to 0 mod p. So, we will state it formally, the Fermat's little theorem. Let p be a prime number, suppose p does not divide a, then a power p minus 1 is congruent to 1 mod p. So, now we will prove this Fermat's little theorem. We begin by considering first p minus 1 positive multiples of a, that is consider the integers a, 2a, 3a and so on p minus 1 into a. As we saw, a is given in our hypothesis which is relatively prime to p, that is GCD of a comma p is 1. So, now what we done is we will multiplied a with 1, multiplied a by 2, multiplied a by 3 and so on, multiplied a by p minus 1. Now, note that none of these numbers is congruent to another modulo p, that is we will prove that part, that is if R A is congruent to S A mod p, where 1 less than or equal to R is less than S less than or equal to p minus 1, as p does not divide a can be cancelled to give R is congruent to S mod p. Cancel means here if you look at R A is congruent to S A mod p means that p divides R A minus S A, that is p divides a into R minus S, but p does not divide a. So, p has to divide R minus S. As we proved one of the properties of prime numbers, if p divides a b, then p divides a or p divides b, from that we will get this. So, now, but which is impossible as S minus R is less than p. Similarly, it is easy to check that none of these numbers is congruent to 0 mod p. Hence, if you consider this set a modulo p, 2a modulo p and so on, p minus 1 into a modulo p, which is exactly equal to 1, 2, 3 and so on p minus 1. Therefore, a into 2a into and so on p minus 1 into a, which is congruent to 1 into 2 into and so on p minus 1 modulo p. So, or equivalently a power p minus 1 into p minus 1 factorial, which is congruent to p minus 1 factorial mod p. Since GCD of p comma p minus 1 factorial is equal to 1, as p minus 1 factorial contains 1 to up to p minus 1, none of them divides p. So, that is why GCD of p comma p minus 1 factorial is 1. Hence, by using previous theorem we have that a power p minus 1 is congruent to 1 mod p, that is what we have to show. Now, one of the important corollary of this result is that if p is prime, then a power p is congruent to a mod p for any integer a. This is one of the nice property of prime numbers. This is true for all a. Earlier, if you look at Fermat's little theorem, there is a condition that the GCD of a comma p should be 1, but here there is no restriction. The proof is very simple. If p divides a, then it is easy to see that p divides a power p minus a, hence the result is true. If p does not divide a, then using the Fermat's little theorem, a power p minus 1 is congruent to 1 mod p. Now, multiplying both sides by a, we will get a power p is congruent to a mod p, hence the proof. Now, we will see alternate proof for this one. The result is clearly true for the case p is equal to 2, as both a and a square have same parity. Here parity means that both a and a square both are even or both are odd. It is easy to see that if a is even, then a square is also even. So, both a and a square are even. If a is odd, a square is odd. So, both a and a square are odd. So, that is what we mean both have same parity. So, in that case automatically p divides a minus a square. Now, let p be any odd prime, then a power p and a have same sign. So, it is sufficient to consider that a is positive. So, we will fix a, we will take a to be positive. So, now fix a prime p and we will prove the result by using induction on a. If a is equal to 1, then it is clearly true, since congruences satisfies reflexive property. Now, assume that result is true for a, that is a power p is congruent to a mod p. Now, we will prove the result for a plus 1, that is we have to show that a plus 1 power p is congruent to a plus 1 mod p. We first observe that since p is prime, p divides p choose k, that is p factorial by k factorial into p minus k factorial for k equal to 1, 2, 3 and so on p minus 1. Hence, a plus 1 whole power p is congruent to a power p plus 1 mod p. But by induction hypothesis we have a power p is congruent to a mod p, hence we get a plus 1 whole power p is congruent to a power p plus 1, which is congruent to a plus 1 mod p. This alternative proof is very useful. It is because here we are getting a plus 1 whole power p is congruent to a power p plus 1. This is one of the nice property for the prime numbers. In this module, we introduced congruences and proved various properties of congruences. Finally, we proved Fermat's little theorem. Fermat's little theorem is very useful for primality testing. That is, for example, if p is a prime number, then we have that a power p is congruent to a mod p for all prime p. But the problem is there are few composite numbers also satisfies this condition. That is why Fermat's little theorem is not sufficient to prove given number is prime or not. But if we have a number, natural number n, and it satisfies a power n is congruent to a mod n for all integers a, then there is a high probability that integer n going to be a prime. With this we will end this module.